What's up, everybody? I'm Jason. Welcome back to the live stream. This week I'm going to be doing something a little different from kind of just rambling randomly about camera stuff. This week I'm going to do some armchair camera engineering. And I mean, I know everybody and their brother or whatever is an armchair camera engineer these days, and everybody can tell everybody how Canon, Sony, Nikon, whoever is doing things wrong or did things wrong or will do things wrong. What I never see from all these people who are clearly know way more than the engineers at Canon and Nikon is the math to support it, the actual engineering. Of course, the excuse that lots of these people will, throw out there is, I don't work for Canon, I don't get paid to do that, I'm not going to do their job for them. And so I don't work for Canon, I don't get paid to do this, and I'm going to do it anyway because I find it interesting. I find it exposes some interesting understanding and interesting information about the camera gear that I use and what it's actually capable of. Sometimes it's shocking how much more well, what's the word I'm looking for? Complex and difficult things are than you expect when you're not you haven't done the math, you haven't stopped and looked at things and so on and so forth. And sometimes it can be very enlightening at just what kind of challenges there are in doing things when you have to think through in say doing things when you have to think through all of the uh, functions, capabilities, etc. of the camera or the device or whatever it may be. So I want to start this off with some disclaimers. I don't work for Canon. I don't work for a competitor of Canon. I don't work for any of the Canon camera companies. I am talking about this stuff purely from my own perspective as an end user who has a little bit of education in engineering and kind of likes digging into things and testing things and trying to understand why things work, how things work, and that kind of thing. Because I don't work for Canon, what that also means is this is going to be kind of hand wavy. I'm going to be doing a lot of meh in this video, largely because, well, the short of it is I don't have access to the internal documentation that somebody at Canon would have for what the capabilities of the hardware are. And as an extension of that, I also don't have the ability to run arbitrary code on my camera. Because, well, if I could run arbitrary code on my camera, I would have implemented things and I'd be telling you this is how it works and this is what it can do. Uh, Finally, I'm sure there's going to be errors in this. So I'm, as I said, not a camera engineer. It's been a long time since I actually had to do silicon level stuff in when I was in school. I did some of that, but that's been a long time now. And the simple reality is, in terms of math, numbers, and computation, I'm trying to make sure that if I'm doing things right, I'm trying to make sure that I've double-checked the numbers and so on and so forth. However, I am not getting paid to do this, and so if I don't have a number right, well, I don't have a number right because the reality is I missed it. And since I'm not being paid to do this, I'm not that concerned about being slightly off somewhere. Now, finally, one thing I want to talk about briefly is my approach to engineering versus what might be done in a lot of other places. So I tend to work at things kind of in the same way that SpaceX does, which is to say, I do the design as much as I can. Well, I do a design, like I don't go into things without any thought at all. I do a design, I'm pretty confident that it'll work, and then I build prototype, and then I fail. Because I almost always don't account for something, or in the case of programming, because my grasp of programming is, well, actually, my whole process with programming comes down to iterate, fail, fix, and iterate again. And that's just sort of the fastest way that I've ever found that I can work when it comes to programming stuff. So if, for instance, I had the ability to write code to run on my camera and efficiently run on my camera, I would have just put this on the camera and seen what I could get it to do, instead of talking through a bunch of theory or like having to pull design docs and stuff like that. Now, that's not to say that somebody at Canon couldn't do this, or somebody at Nikon who wanted to do something, or any of the camera manufacturers couldn't do something similar in that vein and just hammer through, you know, in their spare time, do the thing and get it done. And in terms of what I'm going to be talking about, well, I guess I should, now that I've kind of got the disclaimers out of the way, what I'm going to be talking about today is adding synthetic or computational neutral density capabilities to a camera like the Canon EOS R5. Now, I'm focused on the EOS R5 because the EOS R5 is the camera that I own. And certainly things could be added to other cameras, but since that's what I own, that's what I care about. And the broad spectrum thought is that this is a function that I would like to have, and if it's feasible, I would like Canon to, you know, add it, I guess is really the best way to put it. But that kind of means, like, you know, and I mean, obviously I could suggest it, but that kind of means I'm working within the framework of trying to see if it's something that would be feasible on a camera like the R5. Now, I'm going to talk about some other things in the course of this stream, but that's kind of where I'm coming from. So the question I first start to ask, because this is the first thing you would ever do when you're designing something, engineering something, or just making something, is, you know, what's the problem you're trying to solve, and why do you have this problem that you want to solve it? So the problem, as I said, is implementing synthetic or computational neutral density, which essentially is using the camera's capabilities numerically, so it's a mathematical processing thing, to mimic the behavior of the long exposure that you would get using a a neutral density filter. Now, I recognize right off the bat that, well, it's not going to solve every problem for neutral density use. My specific focus is on these kinds of neutral density filters, as I picked the least dense of the neutral density filters that I have sitting on my desk. These are essentially, that was a 6-stop, and this is a 10-stop neutral density filter, and you use them for long exposures in landscape photography, and they are what they are. So, as I said, I have two filters, two fairly high density neutral density filters. So the question is, why would I want to replace neutral density filters with something in the camera? Well, these are the problems that I have with an optical neutral density filter. To start with, it requires that I have to remember to bring the filter with me. I have to have it. Not only do I have to have it, but I have to have the right one. So if I brought my 10-stop and that's too much density and I really should be using a 6-stop, I can push the ISO up 3 stops, and then I'm compromising on the quality of the, the noise in my images. So I feel these optical filters, I like them, I use them, obviously, but they do have shortcomings. So for starters, like I said, you have to have the filter. On top of that, these are glass filters. I'm not aware, somebody might, but Lee and Breakthrough Photography, which are the two filter brands that I favor, their high density, neutral density filters are glass. They're not plastic. That makes them relatively fragile. They're close to $200 a pop, and that's not something that I really want to break. I'm really nervous about traveling with this, because this is not a super hard case. It's not a crappy case, but I am really nervous about traveling with this case or the other case in my backpack, not having really good hard protection that can't prevent the thing, or that prevents the thing from being flexed this way where it could break. Always a concern in the back of my mind. The whole process is clunky. So I have 4-inch square filters, and for 4-inch filters, you need a filter holder, and the filter holder has filter mounts, and the mounts screw on to your lens, and then the filter holder clips on the mount, and then the filter goes in the holder. And I mean, admittedly, I feel that this is a reasonable solution. You obviously also can get filters that just screw into the lens, and in some cases those are better. They have a better light seal. But in either case, whether you're screwing a filter into the lens or you're using the filter holders, I find the whole system to be clunky. Like, you got to attach the filter to the holder to the camera, or the lens, screw the filter onto the lens, and so on and so forth. And, like, it's just clunky. I mean, it may not be that bad in the grand scheme of things, but I find it to be kind of, clunky. As I said, you also have to have the right filter. So if you only have your 6 and you needed a 10, what do you do? If you have if you need more than 10 for something that you're trying to accomplish, what do you do? Do you even own the right filter? Like, I have a 6 and a 10. I don't have a 3, so if I really needed a 3, well, I could use the 6 and up the ISO by 3 stops, but then I could be in, I'm not shooting at 100, I'm shooting at 800, and I'd rather be shooting at 100 for a landscape kind of thing. So you have that. The next problem, as I see it, is that you can't just dial in more density, if you don't get the results you want. If you need a 2-minute exposure to get the look that you're looking for, but you don't have enough neutral density for more than 30 seconds with your camera and lens, you can't just crank it up. You actually need to have the density, and that's like assuming you're shooting at the lowest ISO. And with modern sensors, you're kind of constrained on how much you can stop it down before you start running into diffraction or real problems with diffraction. The final problem that I have sort of with optical neutral density filters is color shifts. Now, some are good. My breakthrough photography filter is basically, as far as I could see in using it, neutral. It doesn't produce a color cast. The Lee Big Stopper is not quite so good, but I can correct the color balance or color cast in post-processing. And then the high-tech format filter that I had when I first got started with this was so unneutral that I couldn't correct it out. The only thing I could do with it is convert the images to black and white, and that was pretty much the only thing I could do to get a reasonable image. If I just left the image in color and tried to do as much of a correction as possible, I would get just awful color. Now, of course, there are variants or alternatives to a solid neutral density filter, such as variable neutral density filters. Traditionally, they're done with 2 polarizers, and you rotate the polarizers for cross polarization. It works. It's not as susceptible to color shifts as a high density filter. The real problem to me is you have polarizers in the process. Now, good variable neutral density polarizers will let you rotate the whole filter so that you can use that polarizing effect to your ends or to your in your favor. But it does mean that you have to have a polarizer in the path if and if you don't want it, you can't really use a variable neutral density filter for that. And of course, it still has the problem of putting it on the camera, which I'm arguing, and that you have to carry it, that you just can't leave it on the lens because it's a variable neutral density filter. One neat bit of technology in the range of variable neutral density filters is the technology that Sony and Panavision have. Sony in their cinema, what is it, the F series, F whatever, F something or other cameras, and Panavision, I believe it is a externally mountable filter where they're doing electronically controlled variable neutral density filters. And in a huge simplification of how that works, it's basically an LCD monitor. So there's a fixed polarizer, and there's a liquid crystal, and as you increase the voltage across the crystal. It causes the crystal to increase in polarization, and the cross polarization of the crystal and the fixed polarizer has the neutral density effect. So, or it provides neutral, essentially is neutral density. So I'm not saying that that's wrong or bad. It's certainly an option. It's certainly a cool option. However, I also don't particularly think it's the best option. It's, of course, as with many things in engineering, all of these options are options. Variable ND filters have their place. The electronic controlled variable ND filters have their place. Solid ND filters have their place. And synthetic and or computational neutral density being done on the camera has its place. They're not all, it's not one technology completely supplanting another. It's solving a problem or supplanting the technology in certain areas. So what are the benefits of synthetic or computational neutral density? Well, mean stacking for image noise reduction has been something that's been used by astrophotographers to improve the signal to noise ratio for ages. Now, with astrophotographers, what they're doing is they're putting their camera on a telescope, usually on a tracking mount that is exposing for 10, 15, 20, 30, 100, whatever exposures of so many seconds of stars, and the stars are aligned, and then the whole process is averaged, and the averaging process increases the signal where there is signal and decreases the noise where it's just noise. And we can actually see the effect of this noise reduction in stacking using the multi-exposure capabilities on a camera like the R5. So I did a series of test images at ISO 1600, and hang on, I will switch to that. So these are a series of test images in Lightroom that I've shot, and this is just a single exposure at ISO 1600, and the file size is 50.62 megabytes. If I go to a 2-stack average, the file size drops to 49.69 megabytes. If I go to a 4-stack average, it drops to 44.8 or 47.01 megabytes. And if I go to an 8-stack image, it drops to 44.69 megabytes. Now, I know what you're saying, which is like, that's not a lot of savings. Well, okay, let me rewind a second. The reason we can see this in images from a Canon camera is that all Canon RAW files are compressed. And if it's a standard RAW file, it's a lossless compression algorithm. If it's a CR2 or CR3, the CRAW files, then it's a lossy compression algorithm. And the deal with compression is that the more uniform the data is, the better the compression happens. If you had a file that was entirely black, perfectly black, all zeros, it would compress phenomenally well. That doesn't happen, so you don't have to worry about that case. Now, because of the quality of the cameras and so on and so forth, we're not going to see huge drops in compression levels. However, dropping from 50 megabytes basically to 44.5 megabytes reduces the file size by about 12%, which actually is indicative of a pretty good or reasonable increase in noise, or decrease in noise. Additionally, the averaging process reduces noise from all sources, not just some sources. And in some cases, it counters noise that accrues from some sources. So broadly speaking, there's a whole bunch of noise sources in a camera. You have, for example, photon shot noise, which isn't in the camera. It's a property of the light itself. You have read noise, you have conversion noise, you have thermal noise in the sensor, and thermal noise specifically is happening when because of the temperature of the sensor, it randomly is just accruing charge that's not coming from light. Now, the problem with an optical neutral density filter is you're shooting long exposures, and long exposures have a longer time to accrue thermal noise because the camera's warm, the sensor's warm, everything's warm, and there's a longer period of time for the sensor to, especially being, getting hot, accrue charge from noise. Or from thermal noise. Now, when you're averaging, because noise is random, noise averages down and it averages to, I won't say out, but it averages away from being a signal that's in the file. So sometimes pixels will be, or some frames there will be more noise, other frames there will be less noise, and then the average of that will tend towards the sort of, well, it will tend towards the average, but it will tend towards reducing the noise in the overall picture. Now, obviously, noise reduction improves image quality. Less noisy images look better. Reducing the noise, especially in the shadows, also improves dynamic range. Now, this isn't going to be like a 10-stop improvement or anything like that, but dynamic range being the range from essentially clipping, at least in a digital camera, so clipping whites at the top and the noise floor at the bottom. If you can suppress the noise floor even a little, you actually get a pretty good, a reasonable change in dynamic range. Now, on top of that, another benefit of synthesized or computational neutral density is because you're shooting many frames, you can potentially compensate for changes in the scene's exposure, largely because you can basically have every frame essentially be properly exposed. And so as, say, the light levels shift or a cloud throws everything into shadow, each individual frame compensates for that. Now, I've had this happen, and shooting with a 10-stop ND filter, and I ended up where a cloud came in and it covered the whole scene, and it essentially ruined my image, more or less. I was way underexposed for what I needed to be due to the changing light levels, and I didn't have a light meter because I didn't actually own a light meter until I started doing these videos. So I didn't have a light meter to where I could, calculate the additional time needed on the fly. And with a computational approach, the camera can just adjust on the fly. The other advantage that I see in computational neutral density is that you can change the way you approach the control over the neutral density to move it out of the stops domain and move it into the time domain. So as things are now, the way that this works is you meter a scene with your camera, you get, without the filter on it, you get an exposure, you stick the filter on it, and you meter, or you set your exposure time either manually or with a bulb timer or a remote, timer remote or whatever. You set your time to however many stops longer than what you metered when you metered the scene. So I'm not going to get into the details, but I think that gets the thing. So I mean, like if you had a 60th of a second exposure and you had a 2-stop filter, you would shoot for a 15th of a second, to compensate for the 2 stops. With computational neutral density, instead of having to just go with what the time says, because you're not necessarily, it's in an average, or you can divide the number of frames arbitrarily, or have an arbitrary number of frames. You would be able to just tell the camera, I want a 2-minute exposure, and that's it, and no having to figure out, like, if I'm at ISO 100 and I have a shutter speed of X and a aperture of Y, give me a 2-minute exposure, and the camera would shoot as many exposures as it needs to get to that 2 minutes. Now, everything with computational and neutral density isn't all, what do I want to say, roses. There are problems. The biggest problem is that time discontinuities can result in artifacts. And again, we will jump over to the computer. And this is another series of photos that I did as a test. And this picture that we're looking at right now was shot at a 60th of a second. It's a 2-image stack. And it was shot, well, like I said, it was a 2-image stack. It was shot at a 60th of a second. And so there's 2 frames here that are added together. Now, I happen to know that on the EOS R5, because I measured it, the interframe time for a mechanical shutter image, so either the fully mechanical shutter or the first curtain electronic shutter, is between 150 and 150 and 200 milliseconds. It's pretty big gap, actually, if you think about it. I think it might be more like 150 and 180, but, or was it 18 and 20? Hang on a second. I can actually look. Let me look that up so that I'm not making ridiculous comments about performance that is just not wrong or right. Yeah. So it can be as bad as 100. It can be as bad as almost 200 milliseconds. And I mean, that's, you know, a pretty big gap. What happens because you have this gap is things move while the camera isn't exposing. And so you get these kind of double repeated streaks. Now these vertical streaks here are crap on my fan blade. They're not actually artifacts from the multiple exposures, but you could see there's kind of a fan blade here, and then there's another fan blade superimposed on it. And as I lower the exposure or increase the integration time, or lower the shutter speed, so I'm recording more time relative to the interframe gap, you could see I get more blur. And again, you can see the streaking artifact that happens because of the movement of the thing, of the movement of the fan blades in the exposure. But as I increase, now I'm at 1/10 of a second, which would be 100 milliseconds, you start getting rid of you get rid of the artifacts. So that's a problem. Now, essentially, the more exposure time you have compared to interframe gap time, the better your images will turn out. So, you know, if you can shoot 1/4 of a second, so 250 milliseconds with of exposure, and we're doing 2 of those, and there's only 180 milliseconds or 200 milliseconds between the 2 frames, so we've got a 1/2 a second of exposure and less than a fifth of that, or less than 2/5 of that as non-exposure, things start improving. So essentially, that's one of the problems. The other problem is, at least in the traditional approach, and that's where I'm going away from largely in this discussion, in the traditional approach, everything works in powers of 2s, and powers of 2s get to be lots of frames. So if you're doing averaging or multi-shot exposure averaging on your camera, to put some perspective in this, on the R5 or any of Canon's cameras, you can average 8 to 9 frames. 2 exposures is equivalent to 1 stop. 4 exposures is equivalent to 2 stops. 8 exposures is equivalent to 3 stops. That's what the camera will do sort of computationally on its own. Now, with the Canon cameras, you can add another frame, so you could do an 8-stop exposure and then add an 8-stop already computed stack to another 8-stop stack and get 16 exposures, which would be 4 stops. Now, the problem with all of this, especially when you start adding exposures, is that you need you're increasing that interframe gap, because the time that it takes you to set up the addition or the additive exposures, you're not imaging. But this also gets kind of crazy when you start thinking about, like, 32 frames is 5 stops, 64 frames is 6. If you want a 10-stop thing, you're talking about 128 frames. And if you just want to go for however long, you know, you're talking potentially a lot of frames. Now, if you're doing what I'm going to be talking about in the camera, it's not such a big deal. But nobody supports, or nobody makes a camera that I'm aware of that supports doing this in camera. If you're doing it in post-processing, well, it really is a problem, because I tried post-processing a like 500 frame stack using ImageMagick on Linux. I extracted the frames from video because that was the smartest way that I could come up with to shoot them. And ImageMagick just kind of crapped itself and the whole thing crashed, and there was no way that I had enough memory on the computer to deal with it. Now, moving things in camera moves you in software domains from working in 3-color RGB files to working with 1-color raw sensor data, and you're not working at 16 bits, you're working at 12 or 14, or, you know, I mean, I guess potentially 16 if it's a 16-bit camera. But like I said, these are some of the problems that occur with computational neutral density. And of course, the other problem, the last problem, is computational and storage demands, which, since we're asking for the camera to compute something, if it can't compute it, then we can't implement it as, you know, it has to be able to compute it. And that's kind of the question that I'm asking here in the big, broader sense. Now, is there an alternative to this that you could do in camera? And it was suggested by a commenter on my other video on my 10 things that I'd like to see Canon implement, and I had made a comment about, in the R5, and I had made a comment about computational neutral density, and it was suggested in a comment that what we really should have is expanded ISO ranges. So instead of having to use neutral density or do neutral density, you would just be able to crank the ISO down. Now, this sounds interesting, and this is the kind of, not to put the guy that suggested this down, because it's a reasonable suggestion, I think, but it's the kind of thing that I would also kind of expect to see maybe a photographer suggest who doesn't have a lot of background in sensor design. And why I'm not bashing armchair camera engineers, but you have to be careful, and you have to kind of sit down and do the math sometimes. So what the question is, and I'll just say straight up, I don't see this as being viable. So the question is, what sets the base ISO of a camera? Because if you want to lower the base ISO, so 50 or 25 or 12 or something like that, instead of 100, then we need to know what affects that in the sensor. And it's important to realize that we have to think about this in terms of photons per second reaching the sensor and being converted, as opposed to exposures as you normally would say as a camera, as a photographer, because you can change the gain of the sensor, which is what the ISO is doing, to change the relationship between the number of photons the sensor collects to the number of digital value, or the digital value that you have in your picture, and that's, you know, shifting things around. So there's basically two things, and I'm also going to say I'm going to be really hand wavy here because it's been a long time since I've done silicon sensor stuff. But there's basically two things that affect the base ISO of a sensor, its basic sensitivity, and that is the quantum efficiency of the sensor, which is how many photons hit the sensor get converted into electrons or captured as electrons on the pixel, at the pixel, and the full well capacity of the pixel, which is how many electrons the pixel can store from, you know, converted light. So to increase or decrease the base sensitivity, if you're playing with quantum efficiency, you have to decrease the quantum efficiency. So you have to have a less efficient sensor, essentially, because if you aren't increasing the well capacity and you want to make the sensor less sensitive, which is what a lower ISO is, you have to convert fewer of the photons that hit the sensor into captured electrons. Now, obviously, lowering the quantum efficiency means that the sensor converts fewer photons into electrons, which ultimately has a negative impact on how that camera performs in low light conditions. And this isn't something like dual gain can get around or something like that. This is an inherent property of the design of the silicon in the photosite. So if you're, like, basically speaking, yes, you could play with quantum efficiency a little bit, but generally speaking, the trend with cameras has been to get higher quantum efficiencies, because the higher the quantum efficiency, the more signal it captures as opposed to wasting. So if you have a sensor that's got a quantum efficiency of 40% versus a sensor that's got a quantum efficiency of 50%, that 50% sensor sees or can use more of the photons that hit the sensor than that 40% sensor can in the same conditions. Now, on the other hand, the thing that you can do is increase the well capacity. So broadly speaking, well capacity is the point. You know, we talk about saturation, we talk about clipping points. Broadly speaking, that's what is the well capacity. When the sensor is full of charge, full of electrons from converted photons, then it can't hold anymore, and that you've reached the full well capacity or the saturation point. Now, predominantly, this is tied to pixel areas, at least largely. However, there are things that can be done to improve the full well capacity while making smaller pixels with improvements in process technology and so on and so forth. And broadly, what we see is as pixels get smaller, sensors tend towards lower full well capacities. Not always. Sometimes there's, like I said, little shifts, changes in process technology, but based on data from, for example, clarkvision.com, I think it's clarkvision.com, he measured well capacities for the 5D, the 5D Mark II, and the 5D Mark III, and they were around 80,000 electrons for the 5D, and that has 8.2 micron pixels. That dropped to about 66,000 electrons for the 5D Mark II, which has 6.4 micron pixels. And that slightly ticked up to about 69,000 electrons for the 5D Mark III with slightly smaller pixels. So like I said, it's not a perfect, linear relationship. Additionally, pulling some data from photons2photos.net, which is derived from DxOMark testing, which I'm not entirely sure I completely trust, because DxOMark has certainly had issues with the way they test things, and especially with really new Canon cameras. But for Sony's A7R II, they were seeing around, or they calculated around 52,000 electrons. For the R3, it slightly went up to about 54,000 electrons, and for the A7R4, it dropped to around 36,000 electrons. And this is per pixel. And like I said, it's obvious that there's better improvement, or there can be improvements even with a smaller pixel due to improvements in technology, like going to backside illuminated sensors and so on and so forth. But it's not going to be like earth-shattering or world-shattering improvements. Additionally, what we're talking about here is, in these cases, we're talking like 52, 54, 38, 30, like changes that are kind of in the same reasonable or same magnitude range. We're not talking about a sensor going from 50,000 electrons to 100,000 electrons. And there's what the problem is to go from a sensor, if you're not messing with quantum efficiency, you go from a sensor that has a 50,000 electron full well capacity, and you want to basically drop that base ISO a stop, you need to increase the capacity of the well a stop, which means you need to double it. So you'd have to go from 50,000 electron capacity to a capacity of 100,000 electrons. And that's just not something that I see as being super reasonable. On top of that, like I said, all of this stuff has limits. And you can really kind of see the effect of this if you look at what Nikon did with the D850 and the Z7 and Z7 Mark II. They're all extremely closely related sensors in pushing their base ISO down from 100 to 64. And broadly speaking, the problem, if you compare the 850 or the Z7 to the R5 or the A7R Mark III, which was 45-ish megapixels. So we're talking essentially the same size pixels. The Z7 D850 perform have about a half stop less dynamic range than the R5 or the A7 Mark III or the A7R Mark III. Obviously, the R5 is newer. The A7R Mark III is a Sony, and you can make whatever excuses you want. But the reality is, the need to push the performance down. So the D8 or the Z7, the D850, again, they all pretty similar sensors, have slightly larger well capacities than the A7R3, and they have markedly lower quantum efficiency. So again, according to that data from Photons to Photos, from data derived from DxOMark, an A7R3 has about 54,000 electron capacity and about a 59% quantum efficiency, and a Z7 has about 58,000 electron capacity and about a 46% quantum efficiency. And the combination of those two changes really does knock the camera down. It just, there's more room for noise. There's less signal available, or there's less efficiency, and so on and so forth. And likewise, even looking at the A7R4, which is way higher resolution, but still has a really good quantum efficiency, even though the well counts are down, the Z7's dynamic range is about a quarter stop worse than that. And this is kind of across the board. There's little places where it's not that easy or not that direct, but there's kind of room across the board. And so the reality is I don't see any camera manufacturers, barring a major change in technology or a major leap in technology, really pushing ISO sensitivities to the point that it would be indicative of the kind of performance that you would want or need to have really long exposures, 2, 3, 4 minute, 10-minute, hour, whatever exposures that you would get from synthetic or computational neutral density. And it's probably worth pointing out that even if you go into the medium format world, ISO 50, ISO 64 is pretty much the base performance level there, and they have an advantage of obviously of having a much bigger sensor to collect data from. So like I said, we could expand the ISO range, but I don't see that being a really a solution to going for really long exposures. Same thing goes for knocking down the like going to a computational ISO 25, so, or an extended ISO 25. So ISO on most cameras with the base ISO at ISO 100, ISO 50, is you give up a stop of dynamic range essentially, and or it has the same dynamic range essentially as ISO 100, and it's compressed down mathematically. Going to 25, I don't really see, like, I don't really see that being a kind of like long-term goal. Okay, so now that I've rambled about the technical or the non-technical stuff for 45 minutes, let's try to get through the technical stuff. And I may end up breaking this actually into 2 weeks worth of videos, considering how long it's taken to get through what I've gotten through. So let's get on to the engineering. Important thing to understand when talking about engineering is engineering isn't just making things. Makers make things, and makers don't have budgets. Well, they have financial budgets, but they don't really have time budgets. They don't have economic budgets to consider. Engineering is basically looking at what's necessary to make things or something to work, and then framing that in the context of, is it feasible to do that within the available technology and the economics of the product? It would not be of any value to us as photographers if to do computational neutral density you needed the equivalent of a 300 watt GeForce GTX 38 or GeForce RTX 3080, and it would add $1,000+ to the cost of your camera, and you would have to carry around a massive battery pack or a long extension cord to plug it in and use it just for it to work. So we're going to start with sort of the considerations. What do we need to know to actually test these things? And there's couple considerations that I came up with. One is we need to understand the exposure requirements for long exposure neutral density use. Now, as I said, computational neutral density cannot replace all places that neutral density is used. However, there's kind of two regimes that I'm breaking things down into. One is long exposures. So it's landscape photography, cityscape photography used to blur the water, the clouds, cause people in cars to disappear in cityscapes, that kind of thing. And this is kind of exposures longer or much longer than a second. The other side of the equation is short exposures. So I'm going to say less than 1/30th of a second, so faster than 1/30th of a second. And this would be the use where you're trying to deal with the problems caused by using a fast lens in bright conditions, sort of with a limited or fixed shutter speed, basically the situation you have with video. You have to shoot at a 60th of a second. You want to shoot at f1.4, and it's the middle of the day when you're recording this thing, and at ISO 100, you still can't bring the shutter speed down, so you have to have neutral density. The second thing to understand, I think, is the problems associated with the existing stacking solution, either in camera or not. To which end, I would argue that in-camera stacking is ideal. It minimizes the amount of data that has to be processed for, both the camera, a computer after the fact. It also minimizes the amount of data that has to be stored. As I said, if you're doing this in camera, you can work essentially in the raw pixel domain. So 12 to 14 bits of data per pixel. Each pixel is a single color because of the Bayer pattern. You don't have to work in the 24 to 48 bits 3-color RGB land of, you know, things sort of after the fact. Now, you could still do this with raw files on a computer if you had software that could read the raw files and do the stacking without, you know, and then generate essentially a raw file without having to go through the hoops of converting it to TIFFs or PNGs or whatever. Now, one of the problems with the current in-camera multi-shot system is that it has the user interface for stacking, one of the problems with the current multi-shot solution in camera is that it really isn't designed for this kind of continuous exposure thing. There's large time gaps between each frame as a result of cycling the shutter and so on and so forth. And those time gaps result in the artifacting that I talked about earlier. Of course, off-camera stacking solutions tend to, in my experience, fare poorly when faced with a large number of, or a lot of information. So one of the first things that I played with, I briefly touched on this when I got the R5, was shooting a 2-minute video at 8K, because 8K is actually enough information to make a reasonable print from. Shooting a 2-minute video with about a 360-degree shutter angle. Obviously, I care absolutely nothing about rolling shutter because everything's getting averaged together and it just averages things out. But shooting that and then taking it, converting it to PNGs, because I had no better answer at the time, I still don't really, on my server, and running ImageMagic's mean filter to stack all of that into one big stacked image, and that crashed and burned hard. ImageMagic could not deal with that many frames. And of course, the final problem in this area here is that the reality is the camera UIs, in my opinion, aren't really designed for this. The multi-shot UI on Canon's cameras is designed for a lot of stuff. It could do various different things. It can do things creatively, but it's not really designed for, I want to shoot an exposure of X minutes, or I want 10 stops of neutral density. So, with that said, what should a good implementation of stacked computational neutral density do? Well, first of all, it should address the artifacting problem, the visual artifacting problems. So we need to know how much of an interframe delay is acceptable, how much of an interframe delay actually can be, how low of an interframe delay can actually be had on a camera, and so on and so forth. And then the second part is, I'm going to make the argument that this all should be implemented in camera in such a way that the camera doesn't significantly limit the photographer's ability to do things. So not like 8 exposures only or 16 exposures only. It should be allowed, you should be able to go more, and it shouldn't require significant storage in the camera. So like, I'm not shooting 100 or 500 raw images, putting them on the flash card to take up space. Like, I should be able to shoot one computationally neutral density, long blurred exposure, and have the file, have a single file be saved out of that. There is no way I'm going to get through this in a reasonable length of show tonight at all. So this is what I'm going to do. I am going to wrap tonight's stream up here. I'm going to finish this next week in the live stream, or maybe the next 2 weeks, depending on how long it takes me to get through it. Just because I'm trying to I don't want to turn this into a 2 and 3 and 4 hour long stream, single stream, and because I don't have the fatigue levels to sit here and go through a stream for that long talking about something potentially this complicated. So I've talked about why, and I've talked somewhat about what I think should happen. Next week, we're going to actually start talking about, or I'm going to talk about the problems of dealing with artifacting and some implementation, how to do the implementation, and some testing that I have actually done, not on my camera, but on a computer, to kind of figure out how fast, how much computation is involved in doing this. And truthfully, I think next week is going to be really interesting because there is so much stuff that I just learned about my camera, learned about the process, learned about programming, which is interesting because I don't actually work in C++ all that much, but I did write the code for this in C++. So that's what we're going to do next week. I just don't see this as being a something I can get through in the next 30 minutes or an hour. So if you've made it this far, thanks for watching. I will be continuing this next week, so you might want to subscribe. Smash the like button if you found this interesting. I know it kind of ends on a cliffhanger. It's just the way it's got to be due to time. Aside from the live streams, I do these live streams every Friday night at 9 to 9:15. I'm trying to do them at 9 now, just that little bit earlier helps. So if you're interested in this kind of stuff, discussion on camera gear, camera stuff, photography, etc. in general, you know, please consider subscribing. You may want to hit the notification bell because I do post videos, but I don't post them regularly. And so aside from the live streams, if you don't hit the notification bell, you might miss the videos if, or whatever. I don't know why I do this. Every week I do this thing. I trip over my own thoughts trying to say it, and it's like, you're a YouTuber. You know how to YouTube, I hope. Do the YouTube thing. So anyway, thanks for watching again, and I'll see you next week. Later.